Hello and welcome to another Ginger Mathematician video. So I put out a poll very recently about which topics you want me to go through the all of for paper 1, and you can see by a whopping majority here, so 53% compared to the other 4 topics put out there, you want more calculus. You've made that very clear from what we just did on differentiation and moving on to integration. So that's exactly what we're going to do today. We're going to spend about an hour going through very typical integration problems, some easier and some quite difficult. I will do some occasional differentiation questions in it because often it's linked with the integration process. Right, let's get started with a nice easy one to warm myself up. So a curve with equation y equals f of x is such that the f dash of x, so the first derivative of the function, is equal to this here, and we're given some initial conditions here, so f of 8 is equal to 5. So what that means in ordinary language is when x is equal to 8, y is equal to 5. And one thing you need to be aware of on the A-level courses is getting used to the different ways they can express things. Notice they've used function notation here, but they could have written x equals 8, y equals 5 as well. And from this we need to work out f of x, the original function. So whenever I see you're given f dash of x and you want to find f of x, that should be a trigger to do integration. Notice if we were given the function and we need to find f dash of x, then that would be differentiation. Again, check out that video if you haven't been through that already. So in order to work out f of x here, we need to integrate, I'll do this in 2 steps, integrate the derivative with respect to x. So what that means in reality is we're going to integrate this 2x to the power of minus a third minus x to the power of a third dx, like so. So this gives us a chance now to go through the basic integration rules before we look at a more complicated example. So if we want to integrate this, then first of all, the way I tend to do this is I add 1 to my index, so I'm doing minus a third plus 1, and you can think of this as minus a third plus 3 over 3. That then gives us 2 over 3, so we pop 2 over 3 here, and then we divide by the new index, so what we just worked out, so divided by 2/3. I tend to write it out in this sort of stepped approach so we don't make any mistakes. Here we do something very similar, so we add 1 to the index, so a third plus 1 is equal to 4 over 3, and then we divide through by 4 over 3. And hopefully you've remembered this. Don't forget your constant of integration. Here we're doing an indefinite integral. There are no numbers top and bottom, so we have to include in the plus c. Now we just need to sort out these fractions. The way I tend to do this, if we're dividing by 2/3, that's the same as multiplying by 3 over 2. So I tend to write this out also as a second step, particularly if you're getting started out on this. And likewise, we just flip the fraction, so 3 over 4 x to the power of 4 over 3 plus c. Okay, we have a cancellation here, so we get 3x to the power of 2/3 minus 3 over 4 x to the power of 4 over 3 plus c. Now again, we're not finished at this point. We haven't got the full function here, and we need to work out what this c is. So now we use these initial conditions. So when x is equal to 8, y is equal to 5, or f of x is equal to 5. So if we use that, we again get 5 is equal to 3 lots of 8 to the power of 2 over 3. Again, you can use your calculator to help you here as well. And then we have 8 again, to the power of 4 over 3. So wherever I see an x, I put an 8, then plus c. Okay, so we've got the cube root of 8, which is 2. 2 squared is 4. 4 times 3 is 12. Again, if that was quick, okay, just rewind, go down to 0.5 speed so you can listen through that. And if we do this part here, so we've got 3/4. So we have the cube root of 8, which is equal to 2. 2 to the power of 4, that's equal to 16. And I think we're going to get something nice here. So 3/4 of 16 is equal to 12. And boom, the 12's cancel. 12 minus 12 is 0. Therefore, C is equal to 5. So to write our full answer, so make it very clear to the examiner, we're going to copy out what we did before, 3x to the power of 2 over 3 minus 3 over 4 x to the power of 4 over 3 plus 5. You need to have that full function there with C worked out in order to get all 4 marks for that question. Okay, so you can look at the mark scheme there. Again, mark schemes don't give you too much information, so hopefully this video is really helping you understand this integration progress as we go through. Now that was question 1, so you know one of the easiest questions on the paper. However, now we're going to be looking at question 7, so a sort of medium-ish question here. And this is very, very typical. So particularly towards the middle to end of the paper, where they give you a diagram, you need to eventually, in part B, work out the area in between the curve and the curve and the line, or something like that. So the diagram shows the curve with equation 3x minus 2 to the power of a half, and the line y equals a half x plus 1. That's been labelled for us here. And they intersect at points A and B here, and we need to find the coordinates of that. So as soon as I see this word intersect, as soon as I see that, I'm already thinking to myself, equate curve and line in this case. So that's, again, my trigger word. I'm looking for the word intersect, and I'll see that. Usually it means some kind of equating curve and a line. So what do I mean by equating curve and line? Well, I make the curve, so 3x minus 2 to the power of a half equal to the line, so a half x plus 1. So this is just actually equation solving here. Again, it's an important topic throughout all these all-off videos to be able to solve algebraic equations quite effectively. The way I'm going to approach this is I'm going to square both sides. I don't like fractional indices, so if I can remove those straight away, I am going to do that. This cancels, leaving us 3x minus 2. And this is where we have to be very careful. We need to square the entire expression on the right-hand side. So we get a half x plus 1 all squared. So be very careful. If you are simplifying this way, you're squaring everything. You're not just squaring the half x and the 1. One of the biggest mistakes that's made on paper 1. So from there, we're now just going to do some expanding brackets. So remember that this means the same thing as a half x plus 1 times a half x plus 1. So if we use FOIL or eyebrow, there's lots of different ways of describing it. We then get a quarter x squared. I'm going to speed through this a bit. A half x plus a half x, that's equal to 1x. 1 times 1 is 1. Okay, and now we want everything to one side of the equation, so I'm going to minus 3x and plus 2 on both sides. That cancels this through to 0, and the quarter x squared stays as it is. We've got x minus 3x is equal to minus 2x, and then 1 plus 2 is equal to 3. And at the moment, the quadratic is not quite in the form that's easy to solve here. Very well done if you can factorize directly from this. What I like to do is get the coefficient of the x squared to be 1. So all I'm going to do here is just times everything by 4 on both sides. This then gives me x squared minus 8x. 2x times 4 is 8x. 3 times 4 is 12. Again, timesing anything by 0 still leaves you with 0. And now we've got a very nice quadratic here to solve. Again, you should have lots of practice on this. If you need practice on solving factorizing quadratics, then check out my iGCSE algebra video. That'll get you up to speed for sure. In this case, we are going to have minus 6 and minus 2, and therefore x is equal to 2 or 6. We're not finished though, because we have to read the question here, which is it wants the coordinates of A and B. So the easiest thing to do here is take the straight line, because it's the easiest function to work with. This is y equals a half x plus 1. Because notice they intersect at point B. So again, whether we use the first one or second one, it's absolutely fine. And so when x is 2, y is equal to a half lots of 2 plus 1, that's also equal to 2. And when x is 6, y equals a half 6 plus 1, and that's equal to 4. So our final coordinates are, I'll draw this on the diagram in a moment, we've got 2, 2, so 2, 2, and then we've got 6, 4. Always good to check, does this make sense with our diagram here? So this would be 2, 2, because it's closer to the y-axis, and here to be 6, 4. I think that makes conceptual sense from the diagram that we have here. So use that as a double check. If you start getting negatives, for example, then you know you've gone wrong somewhere, and you can go back and check your algebra on that particular part of the question. Now, a very typical thing they ask you, and this is a whopping 5 marks here, is hence. So you have to use part A. So part A is really, really useful to do this part. Find the area of the region enclosed between the curve and the line. Now, the reason that we actually find these intersection points is these tell us our limits of integration. We use the x values, so 2 here and 6 here. So that's the reason we actually spent part A working out those intersection points. So these give me my limits of integration, 6 and 2. And now we look at the diagram here for our integration, and we see which one is bigger than the other, or which one's higher than the other. And notice this curve here at this part is bigger than the line. So when I come to do my integration here, I want to do curve minus line when I integrate. So that's how I get the logic of which way round I want to do this. Higher function minus lower function gives me that area in between. So what that looks like is we're going to be integrating between 6 and 2. The curve is 3x minus 2 to the power of a half, and then the line is a half x plus 1. Be careful with brackets here, the minus applies to the entire function. And here we are, this is the integration we need to do. Now I'm going to show you a kind of short way of doing this integration at the start, because as soon as you start getting functions then with a power outside and you're integrating rather than differentiating, it can get quite tricky. Let me show you my method for integrating this first part here. So the way I think about this is when we integrate normally, like in the first question that we did, we always add 1 to the index. So if I add 1 to the index, a half plus 1 is 3 over 2. So just imagine I have this function, 3x minus 2 to the power of 3 over 2. Now, if you haven't seen my differentiation video, I'd really recommend it because I go through this method a ton. If I wanted to differentiate this, my method would be to take the index, bring it to the front, so we get 3 over 2. Then we derive what's inside the bracket, which is going to be 3. And then we take the entire bracket and reduce the index by 1. 3 over 2 minus 1 is 1 over 2. If I simplify this down, 3 times 3 is 9. 9 over 2, 3x minus 2 to the power of a half. So if I integrate this, so if I integrate this 9 over 2, 3x minus 2 to the power of a half, if I go backwards essentially, I will get to this. However, I've got a 9 over 2 here, whereas here I've got absolutely nothing in the front. So I want there to be a 1 in the front. That's what I mean by nothing here, just a constant 1. So what I think to myself is, what do I multiply 9 over 2 by to give me this 1 at the front? And we've seen this trick actually with coordinate geometry before. All we need to multiply by is 2 over 9, because that cancels and that cancels. So if I integrate this, all I need to do is then put 2 over 9, 3x minus 2 to the power of 3 over 2. This 2 over 9 will cancel with this 9 over 2, and then I get the integration I want. A little task for you, if you don't like, where does this 2 over 9 thing come from? I get that question asked a lot. Regardless, A-level, IB, it just seems so confusing. Best thing to do here is practice, is integration by recognition procedure. And what I'd recommend you to do here is take this function 2 over 9, 3x minus 2. And a little exercise to do, dy by dx, so work out the derivative, and notice you will get back to that answer. And remember, integration and differentiation are just reverse processes. So I take a function, I differentiate it, I take that function, I integrate it, I get back to that initial function. Nice little trick to remember rather than doing some substitution approach instead. Now this part is nice and straightforward to integrate. So a half x, so if integrating a half x, we add 1 to the index, which is 2, and then divide through by the new index, which is 2. If we integrate 1, well, that's just x, so that makes our life easier. Before I start solving this, so I shouldn't put the dx in now. Now we found the integration, and this is between 6 and 2. Let's just tidy this up here. So a half divided by 2. So I get a half divided by 2 again, I get a quarter. So we can then just tidy this up slightly and get 1 over 4. Okay, once we've got that part, then we get the substituting the numbers in. So the way we actually work out our answer, I don't think there's any need to try and simplify this any further, is we start with the 6. So wherever I see an x, I am going to put a 6. Again, notice that's all I'm doing. I'm not going to try and simplify this one down. Notice the brackets here, very important. Plus 6. And then I'm going to do minus and do exactly the same process, but instead of an x here, I'm going to put a 2. So I'm going to get 2 over 9, 3 brackets 2, minus 2 to the power of 3 over 2, minus a quarter, 2 squared plus 2, close brackets. At this point, this is a good thing to practice here. Let's see how well you can use your calculator. Notice how I've written this. I've written this nice and clearly for me, so I'm less likely to make a mistake. So here we go. Okay, just take your time. Do this at home. It's really worth the practice. Getting very familiar with how to use whichever calculator you're using at home. I've got Casio here, which is absolutely fine for what we're doing. So got minus brackets. These fraction buttons really help. In my day, we didn't have these fraction buttons, which was always a bit of a pain. Plus 6, close bracket, minus. Just take your time. Take your time. If you want to fast forward just to the answer, I can totally understand, but I would recommend you just practice this process, because the more practice you get, the better you get at these things. So we've got to the power, that's why you have to be careful, because now it's created a random fraction. Right, so let's try this again. So 2 over 9. Did it find the last time? Open brackets. 3 times 2 minus 2 to the power of 3 over 2. You see how long I'm taking to do this? I'm just watching this very, very carefully. Okay, I finally got there. So if you pop that into your calculator, you can do this in separate steps as well. So you could do this part first, then press equals, and then minus this part. Again, just being very, very careful. And we get our final answer here of 4 over 9. Again, does that make conceptual sense? It's a very small area here. Look at the numbers we're working with. So 4 over 9 makes a lot of sense. So I make it very clear to the examiner. Answer is equal to 4 over 9, like so. Okay, so check your answers here. You can go through everything that we've looked at so far. Try and do leave your answers exact values. Avoid those decimals. Just putting 4 over 9 is perfectly fine. Okay, and on to question 3. So very similar to the very first question that we did, with a little twist in there. So the equation of a curve is such that dy by dx, you're given the derivative, is equal to this expression here. and it's also given that the curve passes through the point 4, 5 over 2. As I said, there's more than one way they can express, in this case, that x is equal to 4 and then y is equal to 5 over 2 on this particular curve. And we need to find the equation of the curve given the derivative. So when we have that situation, again, that should be a trigger to do integration here. So in order to find y, in this case, we need to find the integral of the derivative with respect to x, which in reality just means the integral of this here. And notice we're going to use a technique that we did in the very last question to integrate this thing here in the brackets. So again, what I'd like you to consider here is if we take 4x minus 7, when we normally integrate, we usually increase by 1. So imagine we've actually got 4x minus 7 to the power of 3 over 2 as our function, and we wanted to derive this. Well, if we wanted to differentiate this, we bring the 3 over 2 to the front, we differentiate what's inside the bracket here, so that's going to be the 4, and then we reduce the index by 1. So that's going to be 1 over 2. A little bit of simplification here. Well, 4 times 3 is 12. 12 divided by 2 is equal to 6. So this here becomes 6. And then we get the rest as wanted. Notice, however, we don't have 6 lots of 4x minus 7 to the power of a half. We actually have 3 lots of 4x minus 7 to the power of a half. So now I say to myself, what do I multiply 6 by to get to 3? Well, that's going to be a half. So when I integrate this, let's pop this over here. We do our integration, we're going to have a half, and then this done kind of normally is the way that I describe it. Again, you can check this by differentiating and seeing if it actually works. So this is how I integrate these kind of expressions. Here we work in the normal way. So we go minus 4x, we're going to add 1 to it. So we get plus a half, minus half plus 1 is a half. Then divide by a half. And don't forget, because this is an indefinite integral, we're going to have our plus c. Now we're going to do a little bit of tidying up here. So the first part is fine. Remember, if you divide by a half, it's the same as timesing by 2. So we get minus 8x to the power of a half plus c. And now we can use our initial conditions here. So when x is 4, y is equal to 5 over 2. So we get 5 over 2 is equal to a half. 4 lots of 4 minus 7 to the power of 3 over 2 minus 8. And always make the numbers nice for you. Let's simplify down. Okay, so let's see what we get here. So 5 over 2. 4 times 4 is 16. 16 minus 7 is equal to 9. 9 to the power of 3 over 2. Square root of 9. Again, you can use your calculator here. Square root of 9 is 3. 3 cubed is equal to 27. So we get 27 over 2 here. We've got 4 to the power of a half. That's 2. Minus 2 times 8 is minus 16 plus c. Okay, so let's see what we get here. So if we bring the 27 over 2 to the other side, so minus 27 over 2 on both sides, we get minus 22 over 2 is equal to minus 16 plus c. That means then that minus 11 is equal to minus 16 plus c. And therefore c again must be equal to 5. Must like the number 5 for some reason. Okay, so once we've got that, all we're going to do is write this step out and replace the c with 5. So our final answer here is y is equal to a half 4x minus 7 to the power of 3 over 2 minus 8x to the power of a half plus 5. Notice I'm writing y here rather than f of x because I'm using the notation that they've given me in the question. So going between the two different notations is important to make sure you are being accurate exactly with what you write here. Again, you can check your answer here. Notice they've written, for some reason, I don't understand this, 3 over 6 rather than 1 over 2, but okay, that's absolutely fine. But you can see the method as you go through this particular question. Okay, and on to question 6, and I told you these kind of questions are very, very similar a lot of the time. Again, we've got another line and curve finding area. This time there's a few little twists on this question 6. So we need to find the exact area, so no rushing to our calculators, to find the area bounded by the line and the curve. We still do it in the same way we did the previous question, so we need to work out at the very least the x coordinates of a and b, so we have our limits of integration. And the way that we do that, again, we're not told in the question here, so we don't have that word intersect to help us, but we do equate the two equations here. So we get 5x to the power of a half is equal to 2x plus 2. Let's have a think how we want to go about solving this. We have a couple of different options here. I think we're going to go with one that I've used in my quadratics video. If you haven't checked that out, type in to Ginger Mathematician A-level quadratics and you'll find it there. So we're going to minus this from both sides. So we're going to get 2x minus 5x to the power of a half plus 2 is equal to 0. And we're going to do this by substitution. So we're going to let y equal x to the power of a half. Now, if y is equal to x to the power of a half, if we square both sides, we get y squared is equal to x. Notice if we square, a half times 2 is equal to just 1. Now, the reason we've done that is wherever I see an x, I can replace it with a y squared. So I get 2y squared. Wherever I see an x to the power of a half, I put a y. And notice we've now got it in a comfortable quadratic form. Now it's the practice of your factorising, very, very important skill. Always assume they factorise with paper 1. So we have 2, so we want 2 minuses here. I think we want minus 2 there and a minus 1 there. Again, check those cross terms to make sure that that works, which it does. And therefore that gives us then y is equal to 2, or y is equal to a half. And now we do this called back substitution. So remember, y was equal to x to the power of a half here. So therefore x to the power of a half is equal to 2, or x to the power of a half is equal to a half. And therefore if we square both sides, again we're going to get x is equal to 4, x is equal to a quarter. So nice little use of the quadratics. Again, that's why a lot of these topics, unlike iGCSE, they're kind of integrated, no pun intended here, but they are linked between the different videos. Anyway, we've worked out here, this is a quarter and this is equal to 4. So now we have our limits of integration here. Now notice between a and b, the curve is higher, it's bigger than the line. So when we come to integrate this, we're going to integrate between 4 and a quarter, which is why we worked those out in the first place. And we want curve minus line. So we're going to be integrating between 4 and a quarter. Our curve is 5x to the power of a half minus the line, which is 2x plus 2 dx. And in fact, we can simplify this down a little bit here. Again, not sure if it's necessary. I think it makes things a bit easier to work with. This is just minus 2x minus 2. We're just expanding out the single bracket here. Now this integrates nicely with no reverse chain rule ideas going on here. So if we integrate here, we have 5x, we increase this by 1 to give us 3 over 2, and then we divide by 3 over 2. Here we're going to have minus 2x squared divided by 2, and this is going to become just 2x between our limits of 4 and a quarter. Let's simplify this down slightly before we get started. So this is going to come to the top 2/3, and then if we have 2/3 times 5, that's going to be 10 over 3. So 10 over 3 x to the power of 3 over 2. This cancels here, which is nice. So that gives us minus x squared minus 2x, going between 4 and a quarter. And at this point, we now need to pop in our 4 and a quarter. So I'm going to copy out the first part, wherever I see a 4, x, I'm going to put a 4. So 4 to the power of 3 over 2 minus 4 squared minus 2 lots of 4. And then we're going to do the same thing again. But this time we're going to put a quarter in place. Okay, just being very careful. So squared minus. So be careful not get too excited with your brackets. So 2 lots of a quarter. I suspect you could put this into your calculator straight away, but I'm probably going to simplify it down first here. So 4 to the power of 3 over 2, so that gives me 8. So that gives me, square root of 4 is 2, 2 cubed is 8. So we get 80 over 3 minus 16 minus 8. Here, quarter square root is 1 over 16. And we want to cube that as well. I might just leave this and put this in my calculator. Yeah, it's always that judgment of, okay, how much do I want to put into my calculator? I try and avoid it when I can. But this will give us an exact value. That's what we're looking for. So we're hoping it's not going to be something weird with a decimal. You just want something that's going to be a fraction at the end, which I suspect it will be. That's what they've said in the question. And you can always put 0.25 in your calculator rather than a quarter if it speeds you up slightly. So we have 3 over 2 minus 1 over 16 minus a half. Okay, and we pop it in. And we get our answer of 45 over 16, which is always a good sign. You're not getting a horrible decimal here. They do want it as an exact value. Again, you could also turn this into a mixed number as well. So that would be 2 whole ones. So 16 times 2 is 32, and then 13 over 16. That would also be fine as well. Okay, so you can see the answers that are given here. Again, it has to be an exact value. Okay, that's really important. You can see in the mark scheme they say or equivalent exact answer. That is important to make sure you're getting all 5 marks, which is pretty good, on this fairly tricky paper 1 question. Okay, and on to another question that could look quite familiar to you, because in the differentiation video, which you want to check out, then just check it out above, we went through question 8a, which we did some work on stationary points, if I remember rightly. But here we need to work out the area of the shaded region. Notice we are already given the limits here, so for 1 and 16. It's good to see a question like this, because in this case the curve is actually below the line rather than above the line. Remember, a straight line or horizontal straight line has the equation y equals 5 here, because the y coordinates are both 5. So when we want to integrate this, which we're going to integrate between 1 and 16, so 16 here, 1 there, we're actually going to do it the other way around, not curve minus line, but instead we're going to do line minus curve. So what does it actually look like when we actually put this together? So we have 16 and 1. Now the equation of the line is just y equals 5, so all we need to do here is just write in the number 5, and then we minus the curve, which in this case is x to the power of a half plus 4x to the power of minus a half with respect to x. And like I did in the previous question, all I'm going to do here is just take this minus out, so multiply through this single bracket, just so we don't get confused when we do the integration process. And notice, as I was writing that, I put a plus there, which I have to watch out for, and make sure we put the minus here when we expand the single bracket. Okay, once we've got that, then we can just integrate here. So 5 just integrates to 5x, nice and straightforward. Here we have x to the power of a half. So we want to add 1 to that, so that gives us x to the power of 3 over 2 divided by this new power. Then we do minus 4. We're going to add 1 to the index, that gives us to the power of a half. And minus a half plus 1 is a half. and then we divide through by the new index, and we're integrating between 16 and 1. Let's do a little bit of tidying up here before we continue. So we have 5x, again dividing by 3/2, we can just bring it to the top and flip, so we have 2/3. Hopefully getting used to this technique as we are going through. 4 divided by a half is 8, so we get minus 8x to the power of a half between 16 and 1. And all we need to do now is just substitute in. So we have 16 first of all, so 5 lots of 16 minus 2/3 16 to the power of 3/2 minus 8 16 to the power of a half. And when you do these questions, you should always be glad of the 1. So as soon as you get 1s, your life becomes a lot easier, because 1 to the power of 3/2 is just 1, so this becomes just minus 2/3. 1 to the power of a half is just 1, so we get minus 8. So notice we get a little bit of simplification that we can do as we go along. I'm going to work most of this out without a calculator. So 16 times 5, that's going to equal 80. 16 to the power of 3/2, square root of 16 is 4. 4 cubed is 64, so we're going to get minus 128/3. 16 to the power of a half, that's 4. 4 times minus 8 is minus 32. At this point, I'm just going to leave, I think, most of this alone and let the calculator do the tidying up job for me at this point. So this is an easier one than one we've done already. So we've got our fraction here, minus 32 minus 5 minus 2/3 minus 8. Okay, and we get our answer of 9. Perfect. So again, hard to judge if this looks like 9 in this case, but again, I think a fairly big integer makes some sense there. So you can see the answer here. They've done it slightly differently. They separated out the integration, so just to show you the approach that they took here instead, they essentially worked out this and then just minus 1 from the other, which is also absolutely fine as well. But I'm trying to stick to a consistent approach here of line minus curve, curve minus line. You can see it's the same process again and again, as long as you set it up correctly. Okay, on to question 10 here. If you're liking the content so far with this all of A-level maths P1 integration, then please do like the video. That's the most important thing you can do. And if you're interested in more A-level content, then please do subscribe as well. Right, on to question 10. So you know it's going to be a toughie. The function f is defined by 4x plus 2 to the power of minus 2. X is greater than minus a half. Okay. And we want to integrate between 1 and infinity of the function. Okay, so let's get started on that. So infinity, don't worry about the infinity symbol. It'll sort itself out, it's fine. So 4x plus 2 to the power of minus 2 here. Okay, so with respect to x. So again, I use this process of, okay, if we added 1 to the index, so imagine you had this function to the power of minus 1 and we differentiated. Well, we'd have the minus 1 come to the front. We'd have a times by 4 as well. And then we just reduce the index by 1. So minus 1 times 4 is just minus 4. So 4x plus 2 to the power of minus 2. And here we're working backwards. So notice you've got nothing out the front here. We've just got this 1. So what do you multiply minus 4 by to get just 1? Well, we need to multiply by negative a quarter. Because minus times a minus is a plus. 4 times a quarter is 1. So when we integrate this, so we have to be slightly careful. We then get minus a quarter 4x plus 2 to the power of minus 1. And this is between 1 and infinity. Okay, that seems fine. So then we just need to substitute things in. And even though the infinity seems like, oh God, what's going on here? Let me just rewrite this slightly before we look at this. Notice this is the same as writing minus a quarter multiplied by 1 over 4x plus 2. This is just another way of writing to the power of minus 1, which will help us when we actually work this out. So in order to do this, when we put infinity in, well, if you put a very, very large number into this fraction, eventually this fraction will become 0. So if this becomes then 0, 0 times anything is still 0. So when we put infinity in, we actually get a number out of it. We get the number 0 here. Then we minus, and then we pop in the 1 instead. Okay, this is the easier thing to work out. So minus a quarter, 4 lots of 1, plus 2 to the power of minus 1. Okay, so let's have a look. So 1 times 4 is 4. 4 plus 2 is 6. So we get 1 over 6. So 0 minus a quarter times 1 over 6. And minus 1 over 24. 2 minuses here. So we get 0 minus 1 over 24. You see my face just there, and 2 minuses make a plus, so we just get 1 over 24. If you did get this kind of question in your exam, the key thing is not to be intimidated by this infinity symbol here. The idea is just stay nice and calm, and notice if you have as x tends towards infinity here, so as it goes towards infinity, this fraction 1 over 4x plus 2 will then tend towards 0. So I'm using this idea of limits to help us actually work out a numerical value for when this is approaching infinity. Okay, and on to part B. I like this. I remember reading through this question and going, that's very, very sneaky. And we've seen this idea in a differentiation video as well. That is a differentiation question, but I thought I'd include it in this video as well. So a point is moving along this curve in such a way that as it passes through the point A, its y-coordinate is decreasing at a rate of k units per second, and its x-coordinate is increasing at the same rate. So notice we have the same rate in both, which is very, very important. So if I draw this point on here, and we've got this increasing by this k rate, whatever that is, at the same time it's decreasing at this rate as well. So this point would start here, and after 1 second, after k units, it would then be here. So we've got the A and B, for example, where both of these are k. And if I express it in such a way here, what would the gradient of this line be? Which we tend to use this dy by dx notation now. And notice the gradient is just rise over run. So we're going downwards here. So this would be minus 1, this would be plus 1. And so we get minus 1 divided by 1, which is equal to minus 1. So this very complicated looking sentence here, all it's saying to us is that dy by dx, and let me remove the fraction at the bottom here, is just equal to minus 1. It's a very complicated way. And you've seen this whole tan inverse of 2, for example. Really try to test your understanding here. All they're saying is dy by dx is equal to minus 1. Okay, so if we go back to our initial function here, so our initial function, f of x, because it's moving along this curve, 4x plus 2 to the power of minus 2. So if I differentiate this, so if I do f dash of x, the way to differentiate this, we take the minus 2, bring it to the front, so we get minus 2, differentiate what's in the bracket, that's 4, and then we take the entire bracket and reduce the index by 1, minus 2 minus 1 is equal to minus 3. And if we work this out, we get minus 8, 4x plus 2 to the power of minus 3. And what the question here is saying is that this gradient is also equal to minus 1 as well. So we can equate this with our fact that we just talked about earlier. Therefore, we can say to ourselves minus 8 brackets 4x 2 to the power of minus 3 is equal to minus 1. And now this is just an equation to solve here. First thing I would do is divide through by minus 8. So we get 4x plus 2 to the power of minus 3 is equal to 1 over 8. Then we'll use the idea of reciprocals here. So I'm going to change this to a positive and then flip this fraction, gives me equal to 8. And then we just need to solve this like a standard cubic, really. So the opposite of cubing something is cube rooting. So we're going to cube root both sides. So write this out again. So we're going to do the cube root on both sides. That cancels, leaving us with 4x plus 2. The cube root of 8 is equal to 2 here. And then we get 4x is equal to 0, so x is equal to 0. Not finished again, as I've said in many of these videos, we're looking for the coordinates of A. So we need to work out what the y coordinate is. So let's write this down here. When x is equal to 0, f of 0. So I'm going to go back to my initial function. 4 lots of 0 plus 2. Power of minus 2, that's equal to 2 to the power of minus 2, which is equal a quarter. So therefore, A has the coordinates of 0 and 1 over 4 to give me a lot of marks on this one, all 6 marks on this particular question. Okay, so you can have a look through the mark scheme and you can see where we pick up those B, M and A marks on this question. Okay, and on to another tough question. So we've got another question 10 here on integration. So we've got 2 curves, so with these particular equations down the bottom, and the intersect, so we're told this, which is very helpful, at 0, 1 and 4, 5. And we have to find the area of the region between the 2 curves. Now we've seen lots of questions like this, and this is why you need to practice them. So we've got our limits here, which is between 0 and 4. And this time we've got curve minus curve. Notice this curve is above this one here. So when we write out our integration here, we want to do it between 0 and 4. And we want the first curve, which is this 2x to the power of a half plus 1. So we want that to be the first one here. And then minus everything from the bottom here. So minus a half x squared minus x plus 1 with respect to x. And I like to just get rid of this negative just so we know exactly what we're integrating a bit later on. So plus 1 minus a half x squared plus x minus 1 dx. In fact, you should always look for simplification possibilities here and notice that this simplifies as well, so we don't have to worry about that. Let's go into our integration process here. So we've got 2x to the power of a half, so we add 1 to the index and then divide through by that index. Then we've got minus a half x squared, so we add 1 to the index and then divide through by it. And then we've got x squared divided by 2. Now also be very handy that we've got a 0 here, so lots of things are going to cancel. Let's just simplify this down first of all before we continue. So dividing by 3 over 2 is the same as timesing by 2/3. So that gives us 4/3 x to the power of 3 over 2. This becomes, well, 1/2 times 1/3 is 1 over 6 x cubed, and then this stays the same. Now the great thing is, when we substitute in 0, everything just disappears. So in fact, all we need to worry about here is just putting 4 in. I wonder if we can do this without a calculator. I'm hoping so. I'm really hoping so. So 4 cubed plus, well, 4 squared, 16 divided by 2 is 8. Yeah, I'm going to speed that up. Okay, so let's have a look at what we get here. So the square root of 4 is 2. 2 cubed is 8. 8 times 4 is 32. Divide by 3 is just 32 over 3. Okay, 4 cubed is 64. 64 divided by 6. Oh, That's very handy. That just gives me minus 32 over 3 plus 8. Well, that makes my life a lot easier. So our answer here is just going to be equal to 8, like so. Perfecto. Okay, this is where it gets a bit tricky. I'm sure if you had this in your own exams, you looked at this question and went, don't know what's going on here. So the acute angle between the two tangents at B is denoted by alpha degrees, and the scales on the axes are the same. Find alpha. So let's go right back to our diagram over here. So you'll notice we've got these tangent lines at B, either from the top curve or the bottom curve. So the first thing we need to do is work out the gradients of these particular tangent lines. So let's do that first of all. So we have y equals 2x to the power of a half plus 1. Again, double check. If we differentiate this, we're differentiating here, not integrating. So we're going to bring the half to the front. Half times 2 is just equal to 1. And then we reduce the index by 1. So we get minus a half. And then this part just disappears. If we differentiate the other one, so half x squared minus x plus 1. If we differentiate this, you bring the 2 to the front. 2 times a half is just 1. And reduce it by 1. So that's going to give us just x. Differentiate this gives us minus 1. And the 1 we ignore. But we want to work out the gradient at this specific point when x is equal to 4. So when x is equal to 4, so d by dx, so x is 4, that's equal to 4 to the power of minus a half. Again, you could use your calculator for, but hopefully you know that's equal to a half from all the indices practice that you've done. And then if we differentiate this, when x is 4, then we have d by dx at x is 4. It's 4 minus 1, which is equal to 3. So what do these actual numbers mean? A half and 3. So all I'm saying here is that the gradient of this tangent line, so m here, is equal to a half for this one. Whereas for this one here, you can actually see it from the diagram, it's much steeper. M is equal to 3. So the gradient, the slope of the line is equal to 3. Okay. Now I'm just going to draw out a diagram just to show this in much more detail. So I'm going to draw a nice big line. So this is my m equals 3. I'm going to draw m equals a half, much flatter line here. So this is my m is equal to a half. And we want to work out the angle in between them. So this alpha degrees. Okay, and this is our point here. 4, 5, which is not actually that important, but you'll see what we're going to do later on. Okay, let's think about what a gradient actually means here. So if I get a different color, we can see this a bit better. Let's do this in black. All a gradient means is, as I go one along, how much do we go upwards? So I'm going to take this as an arbitrary, as I go one along. Let's go not so far along. You'll see why a bit later on. So if I go 1 along and up, this would be equivalent to 1 along and a half upwards. Whereas if I do that with the other line, again we're going the same units along here, we're going 1 along, but then we're going 3 upwards as well, so the green represents the 3. Notice we've got two different angles here. We've got this green angle that represents the whole thing, and then we've got this black angle that represents here. And notice, in order to work out this angle, this red angle alpha degrees, we simply need to do the green angle minus the black angle. That's the difference between the two of them. Now you're thinking, but I've got no actual sides to work with here or anything. Well, yes we do, because if I zoom into this green one here and draw this out, where this is 1 and this is 3, we can actually work out this angle using standard trigonometry. Yeah, we can actually say what is going to be tan of theta is equal to opposite over adjacent, which is 3 over 1. So therefore theta is going to equal tan inverse of 3. And we can do the same trick with the black one here as well. This is going to be tan inverse of a half. So to work out this angle, this alpha degrees, we can actually, remember it's in degrees not radians here, then all we need to do is green angle, which is tan inverse 3, and then we just need to subtract the tan inverse of a half. So again, this is all calculator work at this point. So if we go in tan inverse of 3 minus tan inverse 0.5, we'll actually get an exact answer here, which is surprising in some ways, of just then 45 degrees. So again, I didn't put the working actually on here, but then alpha is equal to 45 degrees, like so. So this is a really nice question like this because they're testing your trigonometry skills as well and applying coordinate geometry also to an unfamiliar context. So these question 10s, question 11s, they're great, particularly at the higher end, if you're looking for those higher grades, of practicing 2 or even 3 skills within one particular question. The more experience you get at this, the better you'll get at these style of questions. Okay, so you can see the mark scheme here. So again, you can look through where you pick up all the method marks, there's accuracy marks, the base marks, and so on. And if you want to get your radians, because we just mentioned about degrees and radians, your radian measure up to scratch for A-level maths paper 1, then I suggest you really watch the video right in front of you, because if you've forgotten to revise it, this would be a great thing to cover.